we saw yesterday how DDA works, and so you saw this picture here that should kind of symbolize DDA data. So the MS1 data is this green landscape here, and this is actually the same between DDA and DIA, right? So in principle, there is no fundamental difference in the MS1 data between DDA and DIA. But then, of course, the fragment data, the MSMS data is very different. So in DDA, we are trying to isolate, if possible, single peptides. Of course, it's not always possible. You have co-fragmentation then if you select other peptides together with the one that you wanted to select. But that's the goal, that it's basically single peptides that are selected here. And that's why you have these small mass windows, which are typically below 2 Dalton, 1 Dalton, in this range somewhere. And that's actually very different in DIA. So down here, you see that these windows that that you have, they can be large. I mean, they can also be small, but the idea is that they are first of all fixed, so they don't change their position over like the measurement, and that they cover some range completely, like let's say from 400 to 1000 M/Z or something like this. So you want to cover the whole range. So you have to put windows in there to cover it completely. So they also, you like to have them overlapping a little bit so that you don't completely cut out isotope patterns, so that part of them is only seen in one and the other part only seen in the other. So usually it's good to have a little bit of overlap also for these windows. And then the size of these windows, so that can actually vary a lot. So the size of this window can be, on the one extreme, it could be only one window that covers the whole range, which is kind of the Waters MSE idea. So you would just fragment everything that you have at a certain time point all together, and then let the software do the work and find out which precursors and fragments belong together. So there's no other clue than at least not from the mass window. And you can, on the other extreme, you can have, for example, 2 Dalton windows, which is like the standard size for astral data, for example, right? So they suggest to run it with 2 Dalton windows, and then you would have very many windows. So I think standardly it's like then 300 of these 2 Dalton windows you would need to cover then the whole range, basically, right? So that's a lot of choices one can do there, how to configure the DIA run, basically. And that would then be one circle, right? So one full scan, and then you have these windows appearing, basically, where you fragment. Next full scan windows, but same windows again. Next full, and so on and so forth, basically. So that's the basic idea of DIA. And so our workflow for DIA data is called MaxDIA. Like everything is called max something in MaxQuant. And so this is not really a separate software. You probably have seen already that this is just integrated in. There's only one MaxQuant, and that can do DDA and DIA, right? So it's not a separate software. Yeah, in principle, it's vendor agnostic. But so probably most tested, and what we usually use it for is then Orbitrap, and that could be any kind of Orbitrap model, or timsTOF Pro data, which can also be any kind of configuration of timsTOF Pro. And yeah, so it can be used in library-based mode, where you actually acquire a library. So that could come from, for example, from DDA data of same or similar samples, or the library could also come from DIA samples. So actually, once you make DIA run with MaxQuant, I mean, no matter where this library then came from, you can then export a new library from the DIA data. So it would actually have like the fragment intensities from the DIA samples, right? So you can also use this as a library. But of course, most convenient is not to have to create a library at all. So the library free mode. And so that is then basically using a predicted spectral library. So like with machine learning, a library would be predicted. So ideally for the whole proteome, like you take, for example, all UniProt sequences of, for example, the human proteome, and then you would make the in silico triptych digest, maybe with a miscleavage, and then predict the spectra and also the retention time for all of these peptides in silico, basically, and that would then constitute the library that is basically used behind the scenes for the library-free mode. Right. So then, so it actually contains MaxLFQ algorithm for DIA, and that. So we have seen how it works in DDA, and so the principles are the same in DIA. But we will see later there are some modifications because you can use more information here, because you have more information, because you actually have this independent quantification events from the precursor and from the fragments. And then for the fragments, it's even like for each fragment separately, you already get a quantification. So that kind of we can use then for our advantage to make more accurate quantification with the MaxLFQ algorithm. And then also what is integrated is a machine learning-based scoring. So it's not just the raw score that would be somehow calculated from the one spectrum matching to the raw data and then scoring how good the match is, but it's actually then taking like a feature space of this match, like where things like mass accuracies and or mass errors, better so said, retention time errors, and all kinds of information go in, and then creates a machine learning enhanced score out of this. And we'll also see the details of how this exactly is working soon. Okay, so that's the general overview. And so there are many other things, because we built it into the MaxQuant DDA software, there are many other things, algorithms that we can reuse for DIA. So for example, the way the proteins are grouped into protein groups, or how the FDR is enforced on the protein level. So this is all exactly the same as you know it from MaxQuant DDA. So which is kind of very established way of doing these things. And it's actually then a nice property that you can have exactly the same algorithms and exactly the same standards and applied to your DIA data. So let's see. So let's go a little bit through the workflow. And so that this you saw already yesterday. So in DDA, so one of the things we do is this 3D feature detection, which means nothing else than basically the features are not like scan by scan peaks, but it's actually these objects that are like these hills, like this one here over like mass divided by charge and retention time. So you have this plane, and then the actual peaks are then these kind of hills in this landscape. So here 3D representation, here just a heat map representation of the same thing. And so actually, for if you have ion mobility as well, then you have one more dimension. Ion mobility is actually an additional dimension. So then these three-dimensional objects become four-dimensional objects. Right? So now this is like heat map coded in slices in this three-dimensional space. So like including the color coding, it's then 4 dimensions that you have basically. And here this space is then spanned by M/Z, retention time, and mobility, ion mobility, and then the color coding is intensity. So you have 4 dimensions now, one more than with the regular LCMS MS1 data. And so the new thing then for DIA is that so not only do you have this for the MS1 data, but also in your fragment data, in your MSMS data, you also have these objects now, because like your fragment data is now also continuous in the retention time direction, right? Because you have always these fixed fragmentation windows. So if you take like the fragmentation data that comes from one of these windows, then this also is like exactly the same space of data as you have for the MS1 data. And of course, then for each of these windows, you have then a different space, basically, of this 3 or 4 dimensional data. And so we can then apply the same feature detection also on the fragment data, which is nice because that kind of gets rid of noise and things like this, and also of ambiguity, which kind of yeah, intensity signals belong together and are actually just the same peak measured twice in retention time or in ion mobility direction, basically. So that comes with, so it basically brings the quality of the MS1 data of DDA to the fragment data in DDA. So that's a nice thing that we just get for more or less for free. One has to do a little bit of programming on top, but it's more or less for free coming from the DDA workflow. So that's nice to have thing, basically. So now we have the peptide features. So then, of course, you do the isotoping as you did it for the MS1 data in DDA. You also do the isotoping now in the DIA data. Exactly the same thing, basically. And then the next step would be you have to perform recalibration, like mass recalibration, or also retention time alignment and all of these things. And here, that's actually where it's becoming different from what we do in the DDA workflow. So maybe you remember from yesterday, in the DDA workflow, we are using this principle of doing two searches. So one search is just done for giving us calibrants for the alignment, basically. And then after we correct the data based on this first search, we do the main search. And only the main search is actually performed to obtain identifications that are then used later on in the workflow. So you saw this, maybe you remember this bimodal signal here. So if you plot like the mass error in ppm against retention time, you see kind of this flip-flop behavior. I mean, it's a little bit extreme nonlinearity that you have there, but it does exist. So, I mean, this is a real existing example that we are showing here. And so here you look at the retention time dependence of the mass error in ppm, and here you look at the M/Z dependence of the mass error in ppm. And then we simultaneously fit curves to both of this. Could also be ion mobility, to the ion mobility dependence if there is. And then this is subtracted from the data. And after, so you see here, for example, the mass error histogram looks horrible for this particular example, but it, of course, usually improvable before recalibration. And then after recalibration, you have this nice error distribution that's also much closer to being normally distributed, and it's also much narrower, and it's actually centered at 0. So exactly how you want to have like the residual error after you did some correction to the data. So that's how it works for EDA, and so we don't do this for DIA. I mean, the main reason is that like you don't really have the concept of a search engine that you could just run multiple times in DIA. So we have to do it a little bit differently. And so what we do there, we call the bootstrap DIA workflow for recalibration of data. And so this works like this. You see, it's actually a lengthy chain of algorithmic steps that are applied to the data. And so it always consists of these steps of 3, where first you match from your library. So you're starting with a library. So at the moment, we don't make any assumptions what this library is. Could be in silico predicted, could be measured with DDA, or could also be exported from DIA. So now you have this library. It's just there, basically, right? And you have to then match every spectrum from the library to each DIA sample. So we're looking at one DIA sample at a time, basically, and we match then the library to this particular sample to get the optimal alignment between the library and this particular sample. And then it's for the next sample, it's done separately. So that for each sample, we get the perfect alignment, basically, of the library to the sample. So that way we don't need to align the DIA samples within each other. So we don't need to, for example, adjust the retention times between the DIA samples to each other, but we always adjust like the single DIA sample to the library, and then we go to the next DIA sample and adjust it to the library, basically. So that's the logic of it. And so how do we adjust it to the library? So first we start with a matching from the library spectra to the DIA sample. So we will see later how exactly this matching works. So that's also based then on a score again. But so let's assume now we can do that. So we match the library to the one DIA sample that we're looking at the moment. And this is without any restrictions on, so there's not even any retention time restriction. So we don't assume that you have like the same retention time in library and in your DIA sample. Could be also completely different scale of retention time. And then based on these matches, so this is now done with the stringent score-based cutoff, so not really with FDR basically. So then we can, based on this, we can do linear retention time recalibration, so that we bring the retention times of the library, spectra, and the sample, so that we bring it to the same scale, so that they're both roughly, whatever, 90 minutes, whatever the scale is for the DIA sample. And then, so once we have done this, so then we can apply this recalibrate, so this linear recalibration function, we can apply it to the DIA data. And then now we can look at the retention differences between the library and the sample. So then one would get some histogram like this, and then one would cut this off basically, so that you get rid of the noise of matches that would be like in the next step, the matches that would be outside of this window, because then we know that these are wrong matches basically, right? So based on what we learned from the data so far. And so once we have that, so basically now we have a window of retention time differences after this linear recalibration. And now we can do another round of, so we just, okay, that was our first matching. Now we do a second round, do exactly the same. But now we use this window. So we use a restriction on the retention time. So we use now, so it has to be, the difference has to be within this window that we defined from the data. And so that makes the matching more precise, right? So you eliminate false positives by doing this. And from there on, it's the same. It's just that we adjust different properties in the data. So then the next steps would be linear mass recalibration for the precursors and for the fragments. And then, so this is also then again adjusted, so we can apply these mass shifts to the data and infer window tolerance for the masses as well, right? So it learns then the mass tolerances for precursors and fractions from the data. And so that's then used in the next round of matching. So the next round of matching will be again more specific than it was in the previous step. So now we have, in addition to the retention time window, we have mass windows, and so on and so forth. So we can now, so there you see there are several other steps coming, and in each of these steps you refine one of these variables basically. So for example, there's also, if it's eye mobility data available, then you would also find or determine tolerance windows for the collision cross-section of 1/k0 actually, and then that would also be applied to the data. So that in the final, in the final matching, so that's then similar to in the first search, main search. With the final matching is the thing with which you go ahead into the next steps in MaxDIA basically, right? And then yeah, so it then uses all the nonlinear recalibration functions that it has acquired over this workflow basically. So interesting enough, actually, so you would think then the best you could do with this final data is that you apply all of these tolerance windows to the data, which is also gives you good results basically. But so it depends a little bit on which property you're looking at. But for some of them, it's actually better to remove the restriction again, and then later let the machine learning find out if some match that is actually not in the tolerance window, it's still good, basically, right? So it doesn't necessarily have to be wrong, could be correct still. And then anyway, all of this is then going into the machine learning later to find out what are actually the high quality matches. And then for some of these variables, actually better not to use fixed restrictions. So that actually for masses, it's actually good to use fixed restrictions. But we found it's even better for retention time. It's actually not done actually. So that you just let the machine learning decide if it's a correct match or not. Maybe any questions so far? There's a question.
So in the very beginning, when you were talking about the fragmentation windows that differentiates these data types, is it the instrument that defines where those windows go, or is that the algorithm?
It's the instrument. So,
Right.
but you can of course set them. I mean, then you would have to modify the method that is used there, right? And you could then also choose your own windows basically, but it's done in the instrument.
Thank you.
Okay, so then yeah, here just some results. So there's just one Orbitrap run where we applied this bootstrap workflow, and you see also here looks like in the DDA data you have like before recalibration you have this kind of nonlinear dependence of the mass error in ppm on the m over z of the peptide, and also if you plot it against retention time you also get this nonlinear dependence here, and then after applying the bootstrap workflow, you see that so everything is centered around zero error, and also the systematic dependencies are mostly gone. So it's doing what it's supposed to do, basically. Okay, and then yeah, here you just see the same data again, just in histogram form. So this is the mass error in ppm before recalibration, and that's after recalibration. You see it's shifted to zero, and also like the spread of the histogram, of the error histogram, has shrink, right? So it's has a lower average error than it had before the recalibration. And here you just see the intensity dependence, which is fine, basically. So that's also not showing any systematic effects. Okay, so so that's just the way how we do the recalibration uh, in in MaxQuant. And so here we could have a look at so how does it work regarding the retention time alignment. So part of all of this is that also retention times will be aligned between the library and one particular sample you're looking at, right? And that's again here the case that it always aligns only between library and one sample, and then it goes to the next, aligns between library and sample, and so on. And so we could test this now. If I mean, like the extreme case would be that you use different gradients now. So you have the same sample, but the different gradients. So there's a 30-minute, 60-minute, 90-minute, 120-minute of these. So that's in the DIA samples. And then you have like one fractionated library. Okay, so that was in this case a measured library. And then, so first thing one needs to do is within the library. So this is then processed as DDA data in MaxQuant. So, and then you need to do the retention time alignment within the library itself, right? So you always have to switch on match between runs and retention time alignment. So by switching on match between runs, you switch on retention time alignment if you want to create a library from DDA data in MaxQuant, because then you ensure that within the library already all the retention times are aligned, right? Which you really want, because before you match it to the DIA sample, you first want to make sure that the retention times are consistent within the library already, right? So you need to do retention time alignment within the library. If it is a measured DDA library, right, then you need to do this. Right, and then you see basically the results are then these calibration functions, which are like these curves of highest density in these plots here, and so it found like a separate solution, like for all of these DIA runs separately, and then when we do quantification of these samples, so we just run MaxLFQ. After the retention time alignments, like in DIA, you see that that they're actually very consistently quantified, although they're completely different gradients, right? So that's actually a good thing. So you see very high replicate correlation between the quantification from the different runs. So saying us that if we wanted to, we could even compare DIA samples from different gradients. And with MaxLFQ, you would still get good results out of this. there are no questions to that, there's actually one question over there.
I think different DIA runs. So I'm thinking the experiment, different DIA runs for different sample will be same gradient, but sometimes previous DDA run to create library can be different gradient to salvage more, you know. So in that case, that can be possible if I can run the longer gradient to create library. So retention time maybe in the some information is in the library, but the DIA runs is shorter.
Oh,
but still
that would be one particular example of what we're seeing here. That I mean that's what one would usually do. That you have a long, like 2 hour or whatever for the DDA library generation, and that it's the DIA is short. Right?
Yeah, exactly.
So that's in particular possible. Yes, absolutely.
Okay, thank you.
And it's aligned without. I mean, you don't need any calibrants or something like this, right? So that's just aligned from the data. Okay, so if there are no further questions, let's have a look at how this score is actually calculated. So basically, so we're looking now at like one library spectrum. So first of all, how are these pre-processed? So if it's like a measured library, then first this is consolidated a little bit. So basically, because you have redundancy in the library usually, right? So one peptide is measured multiple times. So first some clustering is performed of the library based on the measured retention time, collision cross-section, if they're present values, otherwise just based on the retention time. So this is for like one peptide sequence modification chart state, basically, right? So you will have multiple versions of these. And so basically the idea is you don't necessarily want to throw them all together because you might have multiple configurations or whatever this is that distinguishes them. For example, the peptide might occur more than once in the retention times, right? So that it kind of elutes once and then another time again. So I mean, that's absolutely possible that you have two of these. And then it's actually not a good thing to average these things because that might be somehow molecules are somehow in different configurations or whatever is happening there. So we don't want to average these. So that means we are doing these clustering based on retention time collision cross-section. And then the fragmentation spectra that are together in one cluster, they are then put together, right? So they're then consolidated together into one consensus spectrum, basically. And from these, we use then some top N intensity fragments to match into the DIA data, right? So then, and to match means now, so in the first step, we don't have restrictions on retention time. That means we have to test all of the retention times. If this library spectrum matches well into the DIA sample at this particular retention time, right? And we have to search basically the retention time. And in steps where there are restrictions on the retention time, one would only test this in an interval, basically, right? Where it's the best match. Okay, so, and if we had eye mobility as well, then we have to test any combination of retention time eye mobility. Basically, so we have to scan this 2D surface here in front. We have to scan this then and find basically the best place where we can put this library spectrum into the DIA sample. Right, so then next thing we need, so we need some kind of score that tells us how good is the match at a certain point, right? So then so how is the score calculated? So you can see this here schematically. So this is a bit different from DDA now. So, you know, in DDA, we are using the Andromeda score to calculate similarity between the theoretical fragments and the actual MSMS spectrum. So theoretically, one could also use Andromeda score here, but one doesn't because that's not optimally performing for DIA data. So instead, one uses a slightly simpler score, which is more or less counting the matches into the data. So like the black horizontal line should symbolize one of these library spectra that we match into the sample. And we just look in the precursor data, in the MS1 data, we just look, is the known M over Z of the precursor, is it found in the data at this particular retention time, right? So here you would find, okay, here there is actually a feature in the MS1 data that would match the precursor mass of this library spectrum. And this could actually be either an isotope pattern, or it could also be single features. So, I mean, there are many features that don't end up in isotope patterns. For example, very low abundant features. They're not always there with at least two isotopic peaks, but we still look for matches also for the peaks that don't end up in isotope patterns, right? So these are actually quite many. So that could be 10 times more than you have isotope patterns in the data. But it's actually to reach high sensitivity, that's actually also important to consider these. So that's in the fragment data, in the precursor data. And then we look into the fragment data for this particular mass window where the library spectrum fits, basically, right? So you have to go to the correct plane, basically, for this particular mass window where the library spectrum would fit in. And then we look into this data as well for matches between the library spectrum peaks and the peaks in this particular MSMS data plane. So here we would, for example, see, okay, the Y2 of the library spectrum, we do indeed find some feature here, which again could be with or without isotope pattern, right? So that's both is looked for. And then we also find the Y4, we find the Y6, and we find the B8. So we find one precursor match and four, 1, 2, 3, 4, 5 matches to fragments, right? So that, I mean, that could be good identification or not. So I mean, 5 is okay, but it's also not brilliant. So ideally, you want to see more matches to the data. But so this is the later dealt with machine learning and statistics and FDR control to see if this is a good match or not with the given forces copy rate. So that's just the first step. So we first determine which features at all are matching to the library spectrum. And then we look, so how well are they actually hit? So that means, so are we in the middle or are we somewhere at the two borders? Or others said, are we at the peak of the intensity of this peak or are we somewhere in the tails of this peak, right? So for example, this guy here, the Y4, so the spectrum or the retention time where we look at the moment is going right through the middle of the peak, right? So it's hitting it at the apex, so that's good, right? So that we should score higher somehow, while the Y6 guy here, so you see it already here, it's more at the border. On this 3D representation, you see it's really hitting it not on top, but in the tail somewhere. Or here, you would see this is somewhere far away from the maximum peak intensity. So that's not so good. So that's actually very likely that this fragment does not, so that these fragments have actually nothing to do with each other. And it's just coincidence that this one here is hit as well, basically, right? So that's why you don't want to score this as good as you score this one. And so the way we do it is, so we add up numbers for these matches, which are between 1 and 0. So it's basically 1 for this guy here. So there you would add 1 because it's like hit at the top. And here you would hit some considerably lower number, could be somewhere around 0.1. And so this number is calculated by the fraction of intensity you have here compared to the highest intensity, right? So you just compare highest intensity to intensity where you hit the peak. So that in this example, it's close to 0.1. So you would add 0.1 to this here, basically. So that's it. So that's the score. So the score will be improved by machine learning later, but this is kind of the raw max LFQ matching score that we apply to the data. And this was applied in all of these bootstrap steps of the alignment workflows, basically. So there we only use these scores, not the machine learning enhanced scores.
There is a question.
Does the mobility data alignment feature in the scoring?
Yeah, so as well. So I mean, this is just an example for LCMS data. If you have like eye mobility, then basically you have to just extend the box in the third dimension, basically, and then it would do exactly the same thing. So it would look if you hit this like 3D surface where the peak is going on, basically, and it would also quantify, assign a number between 0 and 1, depending on how far you are away from the maximum intensity of this peak. So it's exactly the same principle, just everything is happening in one dimension more, basically. There's a question over there.
How many MS2 do you minimum MS2 do you recommend to get the trace data point of the detention?
Yeah, so actually, surprisingly, this can be very little. So actually, it makes a huge difference if you allow for single scan peaks or not. So that in the beginning, we were thinking probably one should be a bit strict with the number of data points for the illusion of a peak, right? Because I think, for example, like in old school, people would say, yeah, but this has to be seen in at least 6 scans or something like this. Otherwise, it's not good, basically. But that's actually not the case. So you get considerably less identifications if you make a restriction like this, right? And I don't think that these are wrong identifications that you get from very short events, because this is all FDR controlled. So I think we can be sure that these are correct identifications. But actually, you have to allow for single scan. I mean, peptides that you only see in one scan, and not before and not after. So you have to allow for that, actually. Otherwise, you lose a lot of sensitivity. And I don't think that's something particular to MaxQuant. That's actually something that Spectronaut is doing all the time already, basically. Okay, so that was the score. And there are actually 2 rounds of scoring. So there's actually a first score and a second score. And so in the second round, we are trying to enforce now, or not trying, we're enforcing now that every feature is used only once. So what does that mean? So here's again an example of how a result from the first scoring could look like. So it could actually be that you have now 2 library spectra. I mean, they're always searched independently against the DIA data. And it could happen that you get a result like this, that you actually have fragments that are hit by the one and by the other library spectrum, right? So like here, actually you have many of those in this particular example, just to exaggerate the effect. We did this basically, but they also have unique ones, right? So these are only matched with the first one, and this is only matched with the second one. And so now we apply some rule so that every fragment is only used for one library, consolidated library spectrum, right? So basically, you see now here that like these matches here, like the lower ones, for the ones that have 2, so they're not here anymore, right? So it's a little bit like the Occam's razor principle that we also apply for non-unique peptides, where we want to decide to which protein groups they belong. It's the same principle. So here we say, okay, the ones that were hit twice or by 2 library spectra, so it's actually more likely that it belongs to the, so if I would have to decide for one, I would say it probably belongs to the one that already has more fragments, unique fragments found, basically. So that way, then almost all of them would go, almost all of the fragments would go to the upper library spectrum, and on the other one would get only one of the fragments. And basically after FDR control, it would probably be gone, right? Because having just matching one fragment is very likely not enough to survive the FDR control later. So with that, we kind of make sure that we don't overinterpret your data, because so these two versions of the peptide could actually be like similar and related to each other. So for example, this could be a peptide that is just distinguished by some modification on a certain site somewhere. Then you would actually have many overlapping fragments and only some of them are different. Or it could be a peptide that is resulting from a SNP and the other one is the wild type peptide. Also there you would have actually many fragments in common and only some of them would distinguish the two versions of the peptide, right? So that's something you have to do to avoid overinterpretation, because if you don't do it, you would just say, okay, I actually have identified both versions of like the SNP, the wild type and the SNP version, which you may not have because there actually was not enough evidence for the independent existence of the other one, right? And you only think there is evidence because you overinterpret the data by using the same feature twice, basically, right? And so these kind of things you can only do if you do actually this higher dimensional feature detection for your fragments, because otherwise you wouldn't even notice that that this match here and that this match here, that they belong together, that they're actually going to the same peak. For that, you need to detect these peaks in like high dimensional ways, basically, right? So that brings us into the position that we actually can enforce this. So if you don't determine the peaks like that, then you also cannot enforce this kind of rule to your data. Okay, so that's the raw scoring. Now we want to go from the raw scores to the machine learning enhanced scores. And so how do we do this? So based on what we get so far, we build up a feature space, right? And then we want to, in this feature space, we want to decide if something is a good match or a bad match. And so this feature space now contains many properties of this matching. So one of them is the score itself. That should, of course, be an important feature, telling you if this was a good or a bad match. But then there are many other things like intensity correlation between the spectrum and the DIA data intensities. And this is there as Pearson correlation and as Spearman correlation. And then there are many other features like precursor charge, retention errors, and so on and so forth. So in total, it's, I think, on the order of 100 features, a bit less, let it be 70 or something like this. I forgot the exact, something below 100. And it's actually, so it's actually, the high number comes from these here. So this is all features that where you have one per match, and here you have multiple of these, like the fragment match score, fragment mass error, and so on. So you have multiple of these because for each fragment that is in this match, you have one of these combination of features. Okay, and then we just do machine learning on these, and it's actually classification. And so what are we trying to distinguish in this machine learning? So classification is always trying to predict some yes, no, or multiple more categorical things. But here's a binary decision. And so what is a decision? So it tries to discriminate like the target and decoy hits, right? So all of this we do with the decoy library as well, which we generate from the target library that is provided. And now we have a classification algorithm learn the decision if something is a target spectrum or something is a decoy spectrum, right? So it's something very similar to what also Percolator would do, for example, with DDA data. And so then we have this machine learning model. And so actually the model itself would actually usually just make this yes/no decision, right? That's not really a score. So we want to have the number that tells us, okay, so based on what you've learned in the machine learning, how likely it is that this is a target or that this is a decoy. So we don't want the yes/no decision from the classification algorithm, but we want a score. But so fortunately, many or most of the classification algorithm also give you a score, like how far are you way off, how far are you in the terrain of the clear decoy or of the clear target hits, basically. And then, so we tried a couple of algorithms. So one of them is XGBoost. We also tried random forest, AdaBoost. Then the neural network here is the fully connected multi-layer neural network, a multi-hidden layer neural network. And then also we just see how good is it just to use the raw score without any machine learning. And then we have 3 different criteria by which we can decide which is the best or the best suited algorithm for this particular data. So one is just to make ROC curves of these decisions, basically. So made in cross-validation, and then you make ROC curves, which you probably have seen. And ROC curves, you always want to be the curve like as close to going vertically up to 1 and then going horizontally to the corner base. So that would be the perfect ROC curve. And then the area under the curve would be, or AUC would be 1 for this ROC curve. And so you want to get as close as possible for this. And if you have a classifier that shows a straight line from here to there, so AUC 0.5, this is kind of random prediction, right? So if you would have like a random predictor, then you would get a straight line. If you have something that is worse than random, then you would actually have a line that is convex like this here, which can actually happen. I mean, sometimes that actually happens, that predictions are worse than random predictions. So that's always funny, but it happens. It's actually quite useful because you can just use this as an anti-predictor. You just say whatever the predictor says, you say the opposite, and then you have a good predictor again, right? So anyway, so what do we see here? So the best curve, so you want to go for biggest area under the curve. The best one is the red one, which is XGBoost. And so with the other 2 criteria, you also find that XGBoost is the best here. And so the other are just, so if you now use this score in MaxQuant, what is the number of peptides that you identify? And what is the number of proteins or protein groups actually that you identify when you use this particular machine learning framework for doing for calculating the enhanced scores, right? And then you see that also here, XGBoost is the winner. And yeah, the others are still better than just raw score, still much better than random prediction, but not as good as XGBoost. And so basically, then that's also what we use. So what then in the end is hard-coded into MaxQuant is that that XGBoost is always used for doing this. And so basically, it's not. So the thing is, it's not just a fixed model that we score, that we put once in front of MaxQuant, but it's always training on the data that you provide. So that means if your data is special in any way, let's say it has some certain fixed modifications or fixed labels or whatever, it would actually always learn from the data that you are using. So it's always suitable for the data. I think there's a question over there.
Standard DDS search, database search, decoy is reverse sequence. I wonder what is a decoy of library? Is that a decoy library has to be intentionally created during the library creation? Or
also, so it's automatically created, and it's basically, so exactly, you cannot exactly do it like it's done in DDA, but it's done slightly differently. So basically, for every library spectrum that you have in the target library, you also have the peptide sequence with it, right? I mean, it's identified, so you know what it is. And then you basically reverse this peptide sequence, but keeping it like cryptic so that it's not easy to detect that it's reversed. So if it was a triptych library, it should remain triptych. And then based on this, the decoy, the M/Z values from the decoy spectrum are rearranged, basically, right? So basically, now give new masses to the decoy spectrum, which is based on this reversal of the sequence.
In MS2.
In what?
Fragment ion.
Yeah, in the fragment ions, exactly. That's the exactly, yeah, a good comment. So you also have to do something to the precursor properties. So basically what you want is that like the decoys follow the same distribution in terms of mass, retention time, and ion mobility. I mean, that's actually very crucial. Otherwise, you could just distinguish target and decoy by looking at the multivariate distribution of these values. And that's exactly what we do. So the decoys don't get exactly the same mass, retention time, ion mobility from the target from which it was generated, but they're changed a little bit. But they're changed in a way that the multivariate distribution of these is preserved, so that you cannot tell from the value of the precursor properties that this is a decoy spectrum. This is actually a profound influence on the FDR estimate. So if you don't do this properly, this has a strong influence on FDR estimates. Okay, so then let's go ahead. So then when we do this, so now the XGBoost is running and it's actually done with cross-validation. So then what it also gives you is the some measure for the importance of the different features. So it actually can tell you as a help to interpret the prediction, it can tell you that which features were actually important for this decision and which were not so important. It's like this one number, which is called gain, and then you can sort your features by this gain number. And so what we found then is that it's actually very interesting that the score, like the raw score that we defined before, is actually not the most important feature, but only the second. It's on second rank. And the most important feature was actually if the precursor ion has an isotope pattern or not, right? I was telling you before that, so we also look at precursors in fragments that don't have an isotope pattern. And this is actually the most important feature for telling if this is a good match or not, basically, right? So one can imagine that whenever you have an isotope pattern for something, that raises the quality of the match, of course, compared to a feature that does not have an isotope pattern, right? So that's why this is an important feature, even more important than the score itself, basically. And the other interesting thing, so retention time error, one probably would have expected that to be there, so that if this is small, that this is likely to be a better match than with a big error in retention time. Number of miscleavages is there. So why is number of miscleavages there? And peptide is not necessarily wrong just because it has a high number of miscleavages. So it's not so much from the matching that it is wrong, but it has a smaller a priori error to be the correct identification in like a normal proteomics run where you try to keep the number of miscleavages low. And then if you find a peptide that has actually 3 miscleavages, then it's actually less likely to be correct than an alternative interpretation where you wouldn't have any miscleavages, right? So that's why this also shows up here. So you see you have actually 2 types of features here. So one is more saying something about the a priori probability in general, like this miscleavages, which has actually nothing to do with the matching itself. And you have then other features that have something to do with the matching itself, like the retention error or something like this. And so they both go in here. Okay, so that was the machine learning part. I don't know if anybody has more questions, maybe.
I was just curious if the precursor having an isotope pattern is like a binarily important thing. Like, does it make it more likely for it to be does the isotope pattern have a specific meaning in the machine learning, or is it just knowing that helps with the increasing the matches?
Yeah, so it finds it out like without putting any more assumption to it. It just finds it out from the data. That is important, and it also makes sense, right? Because if you match to something that doesn't have an isotope pattern, then it has higher chances to be a noise peak, basically, right? So that doesn't even have an isotope pattern, basically, as opposed to actually having an isotope pattern that is actually more confirmation that this is like a real precursor peak, basically, right? So so it did find that out, but it did find that out by itself. We didn't put any more information into the data, right? And then you might wonder, okay, but then if the ones with isotope pattern are so much better than the ones without isotope pattern, why don't we just exclude the ones without isotope pattern? In fact, there's a parameter in MaxQuant where you could do this, but you will get less identifications because, of course, you're less sensitive if you a priori exclude everything that doesn't have an isotope pattern, right? So then, and this is a good compromise that the machine learning is now telling you, okay, even though basically now it can tell you, even though this doesn't have an isotope pattern, but then looking at all the other properties, it looks like that is probably a good identification. That's basically what it does.
Here we have one question.
I wanted to ask about the number of modifications, and are those just the neutral losses, or what if we have a sample that's specifically enriched for modified peptides?
No, so this is actually like really the number of PTMs that are on the peptide, and that's again for a proteome sample. So this is not the phosphoproteome sample where that wouldn't make so much sense. But in the proteome sample, you also, so this has nothing, again, a feature that has nothing to do with the matching itself, but it's again giving you a different a priori probability that this is correct if you have like a non-enriched proteome sample and it tells you this would have 5 modifications, right? So then it's not likely to be correct. If you have an alternative explanation without any modifications, then a priori that even if everything else would be the same matching parameters and everything, you would still say, yeah, but the one without modifications is more likely to be the correct. That's actually very similar to what we do in DDA. So in DDA is what the posterior probability does is exactly the same thing, that it puts all this a priori information into the score. Right? And you have the same here, just done in different ways. So here it's not done with posterior probability, but it's done with the machine learning output.
Thank you.
Okay, so then next topic would be missing values. So I think one would assume that one of the benefits of DIA that it does have less missing values compared to DDA, because it doesn't have the stochastic sampling from like starting with that the machine decides which peptides to fragment, basically. So that's not something that is done in DIA. So that's one of the reasons why one would think there are less missing values in DIA, and that's also the case to some extent. But it's definitely not the case that there would be no missing values. And so also in DIA you have missing values. It's just the extent of missing values tends to be lower than in DDA, and we actually have a way of controlling the number of or the percentage of missing values, which is called transfer Q value. So the number of missing values is not so much a property of the data, but it's a property of the algorithm that you use to define what is a feature that you can use for quantification. So this is a bit similar to the matching between runs that we are using in DDA. So there basically, this is more like a binary thing. So in the first round, we get all the features that we identify by MSMS. And then we add to those the features that we get from matching between runs. And so this is basically more like a continuous version of match between runs for DIA. And so how does it work? So the transfer Q value is a number between 0.01 or the FDR that you're using for peptide identification and 1, right? And so it tries to strike the balance between stringency of quantification and completeness of quantification, right? So meaning in the stringent case, so it is stringent if you put it to 0.01, then it would only allow features for quantification that are identified in this sample by fragment data in this sample, basically, right? While if you put it to one, that is the less stringent one, but the most complete one. So there would also allow to quantify with features that were not identified in this sample, but that were identified in other samples with FGR 0.01 or better, right? And so then in the other samples or in the sample where it was not reaching this the FGR threshold, it's now still put in, and actually then this threshold, like the transfer Q value, is used then. So basically, it means if the peptide has been confidently identified in other samples, it will also be taken here with less stringency. And that, of course, adds valid value. So you restrict, you reduce the number of missing values. But of course, some of them could be wrongly identified. Right? So that's the basic idea. So I guess it's a slightly more convenient solution than match between runs, which is either on or off. But here, actually have a Q value that controls this kind of matching. Okay, then in this plot, you can see what is the influence of the Q value on number of valid values. So it's just 27 replicates. And then we just count for each protein group, how often is it showing up in all of the replicates, then how many protein groups show up in all but one, in all but two, and so on. And you see if you have transfer Q value 1, then this is a flat curve, which means you basically see every protein quantified in almost every sample. So that there's still some very few missing values there, basically. It's essentially a flat curve. While if you do the stringent version, so transfer Q value 0.01, or actually no transfer, that would mean no transfer, then you actually get many more missing values in this case, right? So, and then, I mean, in principle, it's probably good to look at different values for the Q value threshold on your data. So we have something in the middle as a default value, but of course you could then decide yourself, do I want to be more on the stringent side or do I want to be more on the complete side? Right? And you could play around with that parameter. Okay, it's just an example of correlations between replicates. So I mean, that's actually from the original paper where we were significantly better than Spectronaut on the same data, but it's probably a bit outdated. So I think all of the softwares are becoming better and better every day, basically. And but what we're still doing quite good. So I actually have some more recent benchmark data coming in the third part of the talk. Here you see that you can also use the MaxDIA output for absolute quantity or like rough absolute quantification. So we actually compared here, first of all, the MaxDIA IBEC output against the Spectronaut output. And you see relatively good correlation in terms of absolute values between the two. And also, if you compare the IBEC values from MaxQuant against the RPKM values from transcript profiling of the, so with the RNA-seq of the same sample, of the same cell types, then you also see relatively good correlation between the absolute quantifications of IBEC and like mRNA abundances. So I said relatively good correlation, but the R is actually 0.5. But this is exactly the biological variation that you would expect. So you always get something like correlation coefficient 0.5 if you do comparison between like absolute protein abundances and mRNA abundances. So that's kind of confirming that this is doing the correct thing, basically. Okay, so that's the very roughly the quantification output. So let's have a look at the next thing, which is FDR control. So basically, so just to confirm that our internal FDR estimate is okay, we do certain estimate, of independent estimate of FDR with an external method. And so the way this is done is that so we treat basically the software as a black box, and now you offer libraries, like two kinds of libraries at the same time, where only one of them is correct and the other one is incorrect. So you use now two different species, like your samples are from human, and then you use one human library and one, for example, maize library in this case, and then you know everything that matches to maize. I mean, you have to remove the common peptides, only use the peptides that are unique to either of the two, and then you know basically that the hits to maize are false positives. And then it's very similar to the target decoy that one used internally. You can then say that because the libraries were more or less equal size, that you should have the same number of false positives as you find in the maize library, also in the human library, and that's then the way how we estimate the FDR externally. And so what you see here is basically internal and external FDR with the solid and dashed lines, and that's one's for the protein groups, one's for the peptide sequences, and one's for the matches. And you see that so estimates are actually very similar to each other, so meaning that it's likely that this is correct, what we're doing there. And but this was actually for the like measured library of similar samples. So there we get apparently good FDR control. Then like the next question is, what if we do like libraries that are not tailored to the samples? Like we do the full proteome spectral library prediction. So we take all human uniprot sequences because these were human samples, and also the maize because we use this as a like an entrapment or decoy database still. Then we do a prediction of the spectra for all tryptic peptides and up to one miscleavage peptide in this case. And then we repeat the same thing, right? So then we also record like false FDRs, estimated by counting matches to the maize library while the sample is human. And also here we see good agreement on protein group, peptide, and PSM level. So that seems to be a valid thing to do. And that's then, in fact, our way of doing the library free search is basically just making predictions. In this case, with the recurrent neural network from deep math, and use this big library then as an unbiased library to search then samples in the essentially library-free mode. So there are some recent developments on this. So we're actually switching from a recurrent neural network approach to like a non-deep learning approach, which is also based on XGBoost. So XGBoost seems to be some miraculous thing that is good for many things, basically. And also here we use it then for spectral prediction, and we'll hear about much more about this later today, actually, by Shamil. And I think, and so that will also be then the basis of on-the-fly prediction. So like the next version can then also do on-the-fly prediction where one doesn't have to create these libraries externally of MaxQuant, but where MaxQuant just does this. So you but just specify the FASTA file and the rules for digestion, and so everything will then be handled automatically. Okay, so then, yeah, it's time to go for the quantification. And so, as I was already mentioning, we are also using here the MaxLFQ algorithm that you saw already yesterday from Carlo, how it is working on DDA data. And so the difference here is now, so maybe you remember that, yeah, we don't need all of this, but, oh, sorry. But so one important thing is that, so we end up with this triangular matrix of pairwise ratios. So we're always looking for pairwise ratios, and so pairs means sample pairs, right? So we look at all pairs of samples, and then we calculate these ratios for each sample pair. And so these are very accurate because so there's not just dividing total intensities by each other, but we do this separately for all of the peptides, also for different charge states of the peptides, we get independent ratio estimates, and then we take the median of all of these. And that's basically the principle that makes the MaxLFQ algorithm very accurate, right? So that we take these medians. And then there are some more steps how you get then back from this triangular matrix to just one profile, basically here. So there's some other linear regression model done to get back to the profile, but at the heart of it is basically estimating this triangular matrix of ratios. And so this is now where you can do even better with DIA, because now you can say to calculate one of these ratios here, you don't only split between the different peptides of the protein, but for each peptide, now you can take once the precursor intensity, and you can take the fragment intensities, and you can also separate. You can consider the fragment separately, right? You can do it once for B5, then you do it for Y7, and each of them will give you an independent ratio, and then you can put all of these ratios, which is now an order of magnitude more ratios than you had in DDA, into the median calculation, and by this it becomes more accurate, right? So, yeah, so that's the basic idea between MaxLFQ applied to DIA data. Yeah, this is just showing again that so from one peptide you have a lot of independent information now. So I mean, you could already split between charge states in DDA. You could also split between, for example, unmodified and methionine oxidation in DDA. But now you can also split by, you can do it for precursor, then you do it for B3, then you do it for Y5 and Y6. So basically all of the fragments that are in common for the peptide between these two samples that you're looking at the moment, basically, right? So that's basically the idea what that makes it very accurate. Maybe questions?
Quantifying product ions, how does that work for low intensity marginal peaks? Does that introduce a lot of noise?
Yeah, it's a little bit hardware dependent. Very good question. So that's in principle, yes. So we also have filters for that one can apply to the data. So if you go into the settings, you can actually do intensity filters for this. And I would say it's a little bit different if you look at Orbitrap data, or if you look at time of flight data, like timsTOF Pro. So it will be interesting also to see how it will be for Astro, actually, which essentially is time of flight data with a crazy flight path, basically, also for the fragments. So there it's actually, I think it's actually a bit more critical for time of flight data because it's actually sensitive to single ions, right? So it's not really not talking about single cells, but single ions. So one ion already makes a signal in the detector, or can make a signal for timsTOF data. And then actually, not only does it become a bit noisy if you go to the low intensity peaks, but it even becomes discrete because you can see like one ion, two ions. So there's actually a kind of gap between those, right? Which makes it almost like count data if there wasn't a noise, basically. And so indeed, then, so actually we set the intensity thresholds there to kind of exclude the single ion data for quantification. So that's a very good question. Okay, so that answered your question. Are there more? Is there more?
I just had one question about can you get a ratio on the peptide level, or is this only rolled up into a protein level ratio?
I think right now this particular way is rolled up only into protein level, but it would be doable for peptide level as well. I think at the moment for the peptide level, we only have some intensities that you can use there. But I mean, that would be an easy extension also to get the MaxLFQ values reported in the peptide level or also PTM site level. So that's indeed something very useful because you would get like this multiple estimate aggregation for DIA data. You would already get it on the peptide or on the PTMs or on the phosphosite level, which you don't really have in DDA data. Indeed, that would be very useful. But it's not there yet in the current version. Oh, I hope we can pack it into the post-MaxQuant summer school version. Okay, so then maybe let's finish the old benchmark data before we get to the new benchmarks after the break. So this is also something we did in the beginning in the first paper where we wanted to we tried to quantify like a proteome as deep as possible, basically. And for that, we use fractionated, I mean, first of all, fractionated library, which is probably not surprising, but also discovery library, which is library-free mode, and also single-shot library. But we also fractionated DIA samples. So that's something you can do in MaxQuant as well. If you wanted to, you could also fractionate your DIA samples and put them into MaxLFQ, you know, with this fraction assignment that we saw yesterday in DDA. So that is also working for DIA, and then it's only it's matching between fractions and so on. So you can do that in DIA as well. And so then what you see here is that basically with the discovery library, you always get more than with the fractionated library from the same sample. So that's kind of encouraging. That's probably always a good idea to do the library-free mode. So there's not really a penalty from doing this instead of using a library. And we also get, so here you see that the MaxDIA algorithm is actually compatible with the fractionation of the DIA samples, right? So that's what I was just saying, that you actually can do quantification with MaxLFQ between fractionated DIA samples. And here is now, so that's an interesting comparison between RNA-seq data again and the DIA proteomics data. That's again same human cell lines where we now wanted to see. So how I mean, first of all, how deep do we get compared to RNA-seq? But also how good is our FDR? So in terms of, do we actually report many proteins that should not be there, because there's actually also no RNA expression for those. And so for that, we do this bind histogram here. So this, let's look at the histogram first, maybe. So this is a histogram where we bin according to the messenger RNA expression, right? So first we pair the data, so we find corresponding mRNA protein pairs in the data, protein group pairs actually, which is a bit non-trivial, but we will also see this in the multiomics part later, how one does this exactly. And then we make bins according to the mRNA levels, basically, right? So that's what this log2 RPKM is essentially. And so then what you see in the background, so this gray stuff in the background, so you have to imagine this gray histogram is like standing behind all of the other histograms. So there we see what is actually the number of transcripts that are in each of these bins. And so we didn't use the cutoff. So often you cut off the RPKM at 0 because one thinks that there's no reason for the existence of the transcripts that you see with a lower value. So they are not really thought to be translated to proteins or artifacts of the data analysis or any other reason why these are not translated to proteins, basically. And now if we map the proteomics data on this, and this is now, so different colors correspond to different ways it was generated regarding the library that was used. And for example, like the what's this color? This color here. So that corresponds to things that proteins that have been seen with all of the library approaches. And there you see it's so the histogram is not completely filling the RNA, what you get with RNA-seq. But if you use the discovery library, like for example, the green one is in common between discovery library and fractionated library, you get quite close to actually covering everything that you see with RNA-seq in the high abundance bins. And then in the lower abundance bins, actually almost nothing is found there, which is actually a good indication that we have a good FDR control, right? Because these are exactly the transcripts where we shouldn't find any evidence for the existence of the protein, and indeed we don't. So that's actually a good thing that we got almost everything from this high mode here, and we get almost nothing from this like low mode of the distribution. So that's how it's actually supposed to be. And also, basically, we get most out of the libraries that we use. We get most out of the discovery library, which is like the library-free approach, basically.